Welcome to Softly Curious. Tonight, we move slowly into the quiet world of robots. Not the dramatic version, not the loud one, but the version that exists beneath movement, beneath sound, and often beneath notice. This is not a story about the future rushing toward us. It is a story about systems that were already here, waiting. When most people hear the word robot, a very specific image appears. Something shaped like a body. Something that moves with intention. Something that looks as if it might be thinking. But this image is surprisingly recent. Long before machines were expected to resemble us, they were built for a much simpler purpose: to repeat, to endure, and to never grow tired of doing the same thing again. The earliest machines we would now recognize as robotic were not intelligent, and they were never meant to be. They did not decide. They did not adapt. They simply followed motion. Gears turned because other gears turned. Weight shifted because balance demanded it. These systems existed in a space between tool and behavior, not alive but not entirely passive either. In many ways, the idea of a robot was born from impatience, human impatience with repetition, with tasks that required precision but offered no meaning. Long before anyone asked whether a machine could think, the more urgent question was whether it could keep going without complaint. And for a long time, that was enough. What often surprises people is that intelligence was never the foundation of robotics. Control came first. Reliability came second. Intelligence arrived much later, almost as an afterthought. Many systems that we now casually call robots still operate without anything resembling understanding. They react, they adjust within limits, and then they return to waiting. Waiting is one of the least discussed behaviors in machines, yet it occupies most of their existence. A robot spends far more time paused than moving. Sensors remain active. Systems remain powered, but nothing happens. This state is not inactivity. It is readiness, a quiet form of attention that looks like stillness from the outside. Even today, some of the most complex machines in the world spend their lives waiting for a signal that may never come. A temperature change, a proximity threshold, a single variable crossing an invisible line. Until that moment arrives, the robot does nothing at all and does it perfectly. The word robot itself suggests intention, but intention is something we project. Machines do not want to complete tasks. They do not prefer success over failure. They simply move through conditions that either allow an action or block it. What feels purposeful to us is often just consistency executed at scale. This misunderstanding shapes how people talk about robots. We describe them as helpful, dangerous, curious, or obedient. In reality, most robots are closer to mirrors than minds. They reflect the structure of the systems that built them. When a robot behaves unexpectedly, it is rarely because it chose to. It is because something in the structure allowed a different outcome. For a long time, robots were hidden. They lived behind walls, inside machines, beneath factory floors. Their work was loud but unseen, repetitive but essential. Only recently have robots been placed where humans can watch them move. And once visible, they were expected to perform, not just function, but impress. This visibility changed how robots were designed. Movements became smoother. Shapes became familiar. Behavior was adjusted not for efficiency, but for comfort. In some cases, robots were intentionally slowed down so they would not appear threatening. In others, pauses were added so humans could anticipate motion. These changes were not made for the robot. They were made for us. It is easy to forget that most robots were never meant to be noticed. The most successful systems are often the ones you never see. They work in closed environments, repeating the same motion thousands of times with no awareness of outcome. If nothing goes wrong, they remain invisible. And this invisibility is part of what makes robots difficult to define. A robotic system does not need arms, legs, or a voice. It does not even need to move. Some robots exist entirely as controlled processes, monitoring, adjusting, correcting, without ever occupying physical space in the way we imagine. So when we ask what a robot really is, the answer is rarely satisfying. It is not a single thing. It is a relationship between control, motion, and expectation. It is a system that acts without understanding, yet produces results that look deliberate. As we continue, the idea of the robot will become less dramatic and more precise, less mysterious in appearance, but more surprising in behavior. What begins as a simple definition slowly reveals a network of assumptions about intelligence, about work, and about what it means to act without awareness. And quietly, without announcing itself, the robot waits. What makes robots quietly fascinating is not how advanced they appear, but how limited they truly are, and how much can be accomplished within those limits. Many systems described as robots today do not understand their tasks in any meaningful sense. They operate inside carefully defined boundaries, where every possible action has been anticipated long before the machine ever moves. One of the most overlooked facts about robots is that they do not experience complexity the way humans do. A task that feels simple to a person, picking up an object, adjusting grip, changing direction mid-motion, often requires layers of pre-calculated responses in a robotic system. What looks like spontaneity is usually the result of thousands of predefined conditions being checked in rapid succession. This is why robots excel in environments that are stable. A factory floor where distances never change, lighting remains consistent, and objects arrive in predictable orientations allows robots to perform with astonishing accuracy. Remove that stability, and even highly advanced systems begin to struggle. The real skill of robotics has never been adaptability. It has been control. Many people assume robots are constantly thinking while they operate. In reality, most robots spend their time verifying that nothing has changed. Their primary task is not action, but confirmation. Is the object still where it should be? Is the path still clear? Is the signal still valid? If the answer to all of these questions is yes, the robot proceeds. If not, it waits. Waiting, again, becomes the dominant behavior. In large-scale robotic installations, waiting states can account for more than half of operational time. This includes pauses for safety, synchronization with other machines, or simply because the next condition has not yet been met. To an observer, this may look like inefficiency. To a system designer, it is precision. Another common misunderstanding is the idea that robots replace human judgment. In practice, robots inherit human decisions rather than replace them. Every threshold, every tolerance, every acceptable error margin is chosen by a person long before the robot is activated. The machine executes these decisions relentlessly, but it does not question them. This is why two robots performing the same task in different countries can behave very differently. Not because the technology is radically different, but because the assumptions behind it are. Safety margins, acceptable speed, and error tolerance vary depending on cultural, industrial, and regulatory priorities. The robot reflects those priorities without awareness. There is also a quiet distinction between robots that act and robots that observe. Many robotic systems never move at all. Their role is to monitor, measure, and compare. These systems are often embedded deep within infrastructure, checking alignment, pressure, temperature, or flow. When they function correctly, no one notices them. When they fail, their absence suddenly becomes visible. Robots also differ sharply in how they handle mistakes. Humans tend to correct errors intuitively, often without conscious thought. Robots, by contrast, either detect an error within predefined parameters or fail entirely. There is no instinctive recovery. A small deviation outside acceptable limits can bring an entire system to a halt. This fragility is one reason robots are often surrounded by redundancy. Multiple sensors verify the same condition. Parallel systems monitor each other. Fail-safes interrupt motion instantly. What appears smooth and confident on the surface is often supported by layers of caution beneath. It is worth noting that robots are far more predictable than people, but only within the environment they were designed for. Remove them from that environment, and predictability disappears. A robot trained to move objects on a factory line may be helpless in a slightly altered layout. The intelligence people imagine does not transfer. Another surprising fact is that many robots are deliberately limited in their perception. Instead of seeing the world in full detail, they are often restricted to specific cues, edges, contrasts, distances, or signals. This simplification makes systems faster and more reliable. The robot does not need to understand everything, only what matters for the task. This selective perception is one reason robots can outperform humans in narrow domains. They are not distracted. They do not reinterpret instructions. They do not grow bored. They execute the same operation with the same parameters every time, as long as the conditions remain unchanged. Despite popular imagery, humanoid form is rarely practical. Most robots are designed without any resemblance to the human body, because human anatomy evolved for versatility, not efficiency. Wheels, tracks, and fixed arms are often far superior to legs and hands. When robots do resemble humans, it is usually for social reasons, not technical ones. In environments where humans and robots share space, appearance matters. Rounded edges, slower movements, and predictable trajectories are introduced to reduce discomfort. These design choices are not about improving performance. They are about managing human expectations. Robots also operate on very different timescales than humans. Some actions happen in milliseconds, far faster than human reaction. Others unfold over hours or days, with systems maintaining steady operation long after people have left. This temporal disconnect can make robots feel either impatient or strangely calm, depending on perspective. Another quiet truth is that robots do not improve unless something external changes. Unlike humans, who adapt through experience, robots require updates, recalibration, or retraining. Improvement is not organic, it is introduced. Without intervention, a robot will perform the same task in the same way indefinitely. This leads to an interesting paradox. Robots are often described as the future, yet many of them are designed to remain unchanged for years. Stability is valued more than innovation in critical systems. A robot that behaves exactly the same every day is often preferred over one that becomes smarter in unpredictable ways. In recent years, however, this balance has begun to shift. Some systems are now designed to adjust parameters gradually based on accumulated data. Even here, change is tightly constrained. Learning does not mean freedom. It means refinement within boundaries. Another fact rarely mentioned is that robots do not experience failure as an event. A failed action does not register emotionally or cognitively. It is simply a state transition. For humans, failure carries meaning. For robots, it is just another condition to be handled or not. This absence of meaning is what allows robots to operate in environments that humans find unbearable. Repetitive tasks, extreme isolation, hazardous conditions. These do not affect machines in the way they affect people. The robot does not endure. It simply continues. At the same time, robots are deeply dependent on human presence, even when humans are not physically nearby. Design choices, maintenance schedules, remote monitoring, and system updates tie robots continuously to human oversight. Autonomy, in practice, is always partial. As robots become more visible in daily life, expectations rise. People begin to assume intention, awareness, and even personality. These assumptions say more about human perception than about machines. The robot remains what it has always been, a system executing rules at scale. Understanding this does not make robots less interesting. It makes them more so. Their power lies not in imitation of life, but in disciplined limitation. In doing one thing extremely well, without variation, without fatigue, and without complaint. And as we continue deeper into this quiet landscape, it becomes clear that the mystery of robots is not about whether they will become like us. It is about how much of our world already depends on systems that will never understand it, and yet keep it running, silently, all the same. When people imagine a robot at work, they usually imagine motion. Arms moving, wheels turning, decisions unfolding in real time. What rarely comes to mind is that movement is only a small fraction of what robots actually do. Most of a robot's existence passes in silence, in states that look empty but are anything but inactive. A working robot does not move continuously. It waits, it checks, it confirms, then it waits again. Before any motion begins, a chain of conditions must quietly agree with one another. Position must be verified. Limits must be respected. External signals must remain stable. If even one element falls outside tolerance, nothing happens. This is why robots feel slower than expected to those watching them for the first time. Not because they lack speed, but because speed is rarely the priority. Predictability is. A robot that moves too quickly becomes unreadable to humans and dangerous to systems around it. For that reason, many robots are intentionally restrained, even when they are capable of far faster motion. At the core of almost every robot is a loop: sense, compare, decide, act, and then return to sensing. This loop does not resemble human thought. It is closer to a repeated question asked thousands of times per second. Has anything changed? If the answer is no, the robot does nothing at all. Sensors play a much larger role than motors. Cameras, pressure sensors, proximity detectors, force feedback systems. These are the robot's primary connection to the world. Yet even here, perception is narrow. A robot does not see a room. It detects edges, distances, contrasts, or values within a predefined range. Everything else is ignored. This limited perception is not a weakness. It is a design choice. By reducing the world to only what matters for a task, robots become reliable. They are not distracted by irrelevant information. They do not reinterpret instructions. They respond only to what they have been told to notice. One of the most counterintuitive facts about robots is that complexity is often pushed outside the machine. Instead of building a robot that can handle every possible situation, engineers reshape the environment. Floors are leveled. Objects are aligned. Lighting is standardized. The world is simplified, so the robot does not need to be sophisticated. This is why robots thrive in structured spaces. A production line is not just designed for efficiency. It is designed to be legible to machines. When robots are placed into environments that humans navigate easily, but that lack consistency, performance drops sharply. People often assume robots are constantly making decisions. In reality, many robotic systems operate in binary states. Allowed or not allowed. A door is either open or closed. A signal is either present or absent. A position is either within tolerance or outside it. What feels like choice is often just threshold checking. This stands in sharp contrast to how robots are portrayed in films. In stories like Ex Machina, machines appear to hold continuous internal awareness, responding fluidly to conversation and environment. Real robots, by comparison, may freeze entirely if a single expected input fails to arrive. Another quiet truth is that robots rarely initiate action. Most of the time, they are responding. A signal arrives. A condition is met. A sequence begins. Without that trigger, the robot remains inactive. This makes robotic systems extremely sensitive to timing and synchronization with other machines. In environments where multiple robots work together, coordination becomes more important than individual capability. Robots often wait not because they are idle, but because another system has not yet completed its part. Entire networks of machines can be paused by a single unresolved condition. This dependency creates an unusual rhythm, bursts of precise motion followed by long periods of stillness. To a human observer, this can feel unnatural. To a robot, it is normal operation. Robots also do not multitask in the way people imagine. While systems may handle multiple inputs, actions are typically serialized. One step must complete before the next begins. Overlapping motions are carefully controlled to avoid conflict. This cautious sequencing is one reason robotic systems appear deliberate rather than fluid. In many cases, robots are less autonomous than people expect. Human oversight remains constant, even if it is remote or indirect. Parameters are monitored. Logs are reviewed. Performance is evaluated. Autonomy often means the ability to operate without immediate intervention, not the absence of supervision. When errors occur, robots do not improvise. They stop, or they repeat the last known safe state. Recovery usually requires external input. This is why so much effort goes into preventing errors rather than correcting them. A robot that never encounters uncertainty is far easier to manage than one that must respond creatively. This is also why fictional robots feel so different. In films like I, Robot, machines adapt instantly to unexpected situations, blending rule following with intuition. Real robots, by contrast, are built to avoid surprises entirely. Another misunderstood aspect of robotic behavior is energy use. Robots are not always powered at full capacity. Many systems operate in low-energy states while waiting, waking only when needed. This contributes to the impression of dormancy, even though monitoring continues uninterrupted. Time itself is experienced differently by machines. A robot can execute thousands of checks in the span of a second, yet remain motionless for hours. Action is compressed. Waiting is extended. From the outside, this imbalance can feel unsettling, as if intention has been suspended. As robots move into spaces shared with humans, these characteristics become more visible. Deliberate pauses, cautious trajectories, and frequent stops are not signs of confusion. They are signs of constraint. The robot is constantly verifying that it is allowed to continue. Understanding how robots actually work replaces drama with something quieter but more interesting. A world where action is rare, waiting is constant, and precision depends less on intelligence than on restraint. And beneath every movement, beneath every visible task, there is a system asking the same question again and again, patiently, without urgency. Is it time yet? What remains mostly invisible in robotic systems is not movement, but governance. Every pause, every hesitation, every seemingly cautious adjustment is the result of layers of rules designed to prevent a single outcome: uncontrolled behavior. Robots are not built to explore freedom. They are built to avoid uncertainty. One of the most significant structures shaping robotic behavior is the safety envelope. This is not a physical boundary, but a conceptual one. It defines where a robot is allowed to move, how fast it may do so, and under what conditions motion must immediately stop. These envelopes are constantly recalculated, especially in environments where humans are present. In shared spaces, robots often operate under reduced capabilities. Speeds are lowered, forces are capped, paths are constrained. The robot becomes less efficient by design. This is not a flaw. It is a deliberate trade-off that prioritizes predictability over performance. What many people find surprising is that a robot's awareness of humans is rarely sophisticated. The machine does not recognize intention or emotion. Instead, It detects presence, distance, and motion within predefined thresholds. A human stepping closer is not understood as curiosity or urgency. It is simply a variable crossing a line. When that line is crossed, behavior changes instantly. Motion slows or stops. Systems recalculate. In some cases, the robot retreats slightly, not out of fear, but because retreat is the safest permitted response. These reactions can appear almost polite, even cautious, though they are entirely mechanical. Another quiet fact is that many robots are designed to fail safely rather than succeed aggressively. If uncertainty increases beyond acceptable limits, the preferred outcome is inactivity. This is why robots often stop entirely when something unexpected occurs. Continuing without certainty is considered more dangerous than doing nothing at all. This design philosophy extends to collaboration between machines. In coordinated systems, robots constantly wait for confirmation that other components have completed their tasks. A single delayed signal can ripple through an entire operation, bringing everything to a pause. To an outside observer, this may look inefficient. To engineers, it is stability. Robotic coordination also reveals how little autonomy individual machines possess. Decisions are often centralized or distributed according to strict protocols. A robot rarely has the authority to override these structures. Even highly advanced systems operate within permission frameworks defined long before deployment. This is especially evident in large-scale installations, where robots may be separated by significant distances but remain tightly synchronized. Timing becomes as important as position. A robot may wait for hours simply because another system has not yet reached its expected state. Another aspect rarely discussed is calibration. Robots do not assume the world remains consistent. They regularly verify their own position, alignment, and accuracy. These checks happen quietly, often without visible movement. Calibration routines ensure that precision remains within acceptable bounds over time. Environmental drift is a constant concern. Floors shift, temperatures change, components wear down. Robots compensate for these changes through continual measurement. When compensation is no longer sufficient, systems halt and request maintenance. This is not failure. It is compliance with limits. Robots also rely heavily on redundancy. Critical sensors are duplicated. Signals are cross-checked. Systems watch themselves. This self-monitoring does not imply awareness, but it does create a form of internal vigilance. The robot is always confirming that it is still allowed to be what it is. Energy management plays a subtle role in robotic behavior. Many robots operate in varying power states, adjusting consumption based on activity. Waiting is not only safer, it is also efficient. Power is conserved, heat is reduced, and components experience less stress. In some environments, robots are expected to operate continuously for extended periods. Here, reliability outweighs innovation. Systems are intentionally kept simple, even when more advanced alternatives exist. Predictable performance is valued more than novelty. This conservatism can feel counterintuitive in a field associated with progress. Yet many of the most successful robotic systems are those that change the least. Updates are introduced cautiously. New capabilities are tested extensively before deployment. Stability is earned slowly. A common misconception is that robots operate independently once they are activated. In reality, most robotic systems remain tightly connected to networks of oversight. Data flows continuously to monitoring systems, alerts are generated, and performance is constantly evaluated. Even when no human is physically present, human decisions remain embedded in thresholds, limits, and permissions. Robots may appear alone, but they are rarely unsupervised. This creates a particular form of autonomy. Robots act freely only within boundaries that have been carefully defined in advance. Freedom, in this context, does not mean the absence of rules, but the ability to operate without interruption, as long as conditions remain acceptable. When robots move into public spaces, this becomes visible through pauses, refusals, and cautious behavior. What may feel like hesitation to humans is often strict compliance with priorities that favor safety over efficiency. They also experience time differently. Milliseconds matter during sensing, seconds during motion planning, and hours during operation cycles. In environments without humans, constraints may loosen and performance may increase, while in visible spaces, clarity often replaces speed. This trade-off explains why robots feel so different from their cinematic counterparts. Their strength lies not in decisiveness, but in restraint, in acting only when permitted and waiting the rest of the time. In that quiet discipline, robots reveal what they truly are: systems of controlled possibility, moving only when the world allows it. When people ask whether robots can think, the question itself already carries a human assumption. Thinking, as we experience it, is inseparable from uncertainty, memory, and intention. Robots operate in a very different space, where none of these elements exist in the same way, even when the behavior looks convincing from the outside. What often appears as thought is usually structured response. A robot does not weigh possibilities. It checks conditions. It does not hesitate. It waits until permission is granted. The pause that feels reflective to a human observer is often nothing more than a system verifying that the world still matches its expectations. Memory, too, behaves differently. Human memory is shaped by meaning, emotion, and association. Robotic memory is literal. It stores values, states, and parameters without preference or context. A robot can recall 1,000 previous operations without remembering any of them in the human sense. There is no last time for a machine, only the current state compared against stored reference points. This leads to one of the quietest but most surprising facts about robots. Repetition never becomes familiarity. A task performed for the first time and a task performed for the 10,000th time are identical experiences. There is no improvement through comfort, no decline through boredom. Consistency remains unchanged unless the system itself is altered from the outside. Learning, when it exists, is often misunderstood. In robotic systems, learning usually means adjustment within strict limits. Parameters shift slightly. Thresholds are refined. Patterns are weighted differently, but nothing is reinterpreted. The robot does not understand why an adjustment improves performance. It only registers that certain configurations lead to fewer interruptions. This is why robotic learning feels both impressive and shallow at the same time. A system may outperform humans in narrow tasks while remaining incapable of explaining what it has done. The result exists without awareness of the process. For humans, this feels uncanny. For the machine, it is irrelevant. Another subtle difference lies in how errors are experienced. Humans notice mistakes because they conflict with intention. Robots notice errors only when predefined conditions are violated. An unexpected outcome is not surprising. It is simply outside acceptable bounds. When that happens, the system either compensates or stops. There is no reflection, no correction beyond what was already permitted. Decision-making follows a similar pattern. What looks like choice is often prioritization, encoded long before operation begins. If multiple actions are possible, the order in which they are evaluated is fixed. The robot does not choose the best option. It selects the first acceptable one according to its rules. This creates behavior that feels decisive, but is actually constrained. The robot moves forward not because it prefers one path over another, but because one path remains allowed while the others do not. From the outside, this distinction is invisible. One of the reasons robots feel intelligent is that they are extremely consistent. Humans associate consistency with understanding. In reality, consistency in machines comes from limitation. By narrowing what is possible, Robots avoid ambiguity. They do not need to interpret the world. They need only confirm it. As robotic systems become more complex, these distinctions become harder to notice. Interfaces are smoothed. Responses are delayed to feel natural. Feedback is shaped to resemble intention. Yet beneath these layers, the structure remains unchanged. No matter how advanced the system appears, it does not experience doubt. This absence of doubt is both a strength and a boundary. Robots can operate without hesitation in environments where humans would second-guess themselves. At the same time, they cannot step beyond what has been defined. Curiosity, in the human sense, does not exist. Exploration happens only when explicitly allowed. Perhaps the most misleading aspect of robotic intelligence is how easily humans fill in the gaps. A pause becomes contemplation. A correction becomes learning. A smooth sequence becomes intention. These interpretations are natural, but they are projections. Robots do not wonder if they are correct. They do not feel confidence or uncertainty. They exist entirely within the present state of the system and the constraints that surround it. What feels alive is often just alignment between expectation and outcome. As we move further, the line between appearing intelligent and being intelligent becomes increasingly thin. The more refined robotic behavior becomes, the easier it is to forget how little awareness is actually involved. And somewhere within that tension, between behavior that convinces and processes that do not care, the quiet mystery of robotic intelligence begins to take shape. What makes robots feel increasingly mysterious is not that they are becoming more human, but that their limitations are becoming harder to see. Early machines revealed their nature immediately. Their movements were rigid. Their pauses were obvious. Their boundaries were visible. Modern systems, by contrast, are designed to hide their edges. And when limits become invisible, humans begin to imagine depth where there is none. One of the strongest sources of this illusion is continuity. Humans associate intelligence with smoothness. When behavior unfolds without interruption, we assume intention is guiding it. Robots take advantage of this assumption unintentionally. When sensors, processors, and actuators are well synchronized, actions appear fluid. The system is not deciding moment by moment. It is executing a prepared sequence without friction. Another contributor is timing. Humans read meaning into pauses. A brief delay before action feels like consideration. In robotic systems, delays often exist for safety, synchronization, or verification. Yet to an observer, that pause resembles thought. The longer systems operate alongside humans, the more these interpretations accumulate. Language interfaces deepen this effect. When robots respond to speech or text, people instinctively assume comprehension. In reality, most systems map inputs to responses through layers of pattern recognition. Words are treated as signals, not symbols. Meaning is inferred statistically, not understood. Still, the output can feel convincing enough to invite trust. This gap between appearance and process is where much of the modern fascination with robots lives. The system does not know what it has said. It does not reflect on its response. It does not remember the conversation as an experience. Yet the interaction feels real enough to trigger social instincts in the listener. Another quiet fact is that robots do not form internal models of the world the way humans do. Instead of understanding environments as coherent wholes, they operate with fragmented representations. A surface is not a table. It is a plane at a certain height. A person is not an individual. It is a moving shape with specific properties. These abstractions are sufficient for action, but they do not accumulate into understanding. This fragmentation explains why robots can perform impressively in narrow contexts and fail unexpectedly outside them. Without a holistic model, transfer becomes difficult. A system trained to recognize objects in one setting may struggle in another, even if the objects are the same. Context, for humans, is intuitive. For robots, it must be explicitly encoded. The absence of self-modeling further limits robotic awareness. Humans constantly update an internal sense of themselves, where they are, what they can do, what they intend to do next. Robots, by contrast, track states without identity. Position is known, but not experienced. Capability is calculated, but not felt. There is no sense of, I am doing this. Because of this, robots cannot be surprised. Surprise requires expectation and violation. While robots can detect mismatches between predicted and observed states, this does not produce a subjective reaction. The system simply adjusts or stops. The emotional weight humans attach to surprise does not exist. Curiosity is another projection. When robots explore environments or test variations, it is tempting to describe this as curiosity. In reality, exploration is usually the result of optimization routines. The system is searching parameter space, not seeking novelty. Newness has no intrinsic value unless it improves performance. Even when robots are designed to learn, the learning process lacks narrative. Humans learn through stories, mistakes, successes, moments of insight. Robots update weights, adjust thresholds, refine probabilities. The improvement is measurable, but meaningless to the system itself. There is no sense of progress. This absence of narrative is one reason robots struggle with explanation. A system may reach a conclusion without being able to describe how. The steps exist mathematically, but not conceptually. For humans, explanation is a core component of understanding. For robots, it is optional. As systems grow more complex, this gap widens. Advanced models may produce accurate results while becoming less interpretable. The better they perform, the harder it becomes to trace why. This creates a new kind of mystery, not because the robot understands more, but because humans understand it less. Another layer of confusion comes from anthropomorphic design. Faces, voices, gestures. These elements encourage social interpretation. People respond to eye contact, tone, and rhythm instinctively. When robots adopt these cues, they activate deeply rooted human behaviors. The response feels natural, even when the source is mechanical. This effect can be powerful enough to override knowledge. Even people who understand how robots work may find themselves reacting emotionally. A polite pause feels respectful. A delayed response feels thoughtful. These reactions occur automatically before rational analysis intervenes. Yet beneath these surfaces, the internal structure remains unchanged. The robot does not experience politeness. It does not feel respect. These qualities exist entirely in the perception of the observer. One of the most persistent misconceptions about robots is the idea that their intelligence is slowly approaching human consciousness. In reality, the two are built on entirely different foundations. Human consciousness emerges from biology, emotion, memory, and survival. Robotic systems, no matter how advanced, are engineered for function, efficiency, and control. When robots display behaviors that resemble human thinking, it is similarity of output, not similarity of experience. This difference becomes especially clear when things go wrong. Humans experience failure as frustration, confusion, or regret. Robots experience failure as a state change. An error does not carry meaning. It simply triggers a response or a halt. There is no internal awareness of loss, no sense that something should have gone differently. Failure exists only as a condition to be managed. Autonomy often deepens the illusion. A robot operating without visible supervision can feel independent, even intentional. Yet this independence is always conditional. It exists only while the environment remains within acceptable limits. When those limits are crossed, autonomy disappears into waiting. Paradoxically, the more capable a robot appears, the more carefully constrained it usually is. As responsibility increases, safeguards multiply, and freedom narrows. Humans naturally interpret smooth behavior as agency. When a machine moves confidently and adapts within limits, belief quietly follows. Presence is felt, even when awareness is absent. When alignment holds, the illusion remains intact. When it breaks, the structure beneath becomes visible again. Understanding this does not diminish robots. It clarifies them. Their strength lies not in thought or feeling, but in consistency applied at scale. In the meaning we project onto them, robots reveal their most enduring role, not as minds, but as mirrors. Robots are often described as perfect, precise, unwavering, capable of repeating the same action endlessly without deviation. And in many ways, this description is accurate, but it hides something important. The precision we admire in robots does not come from flexibility, it comes from limitation. A robot is precise because it is allowed to be precise only within a very narrow space. To understand this, it helps to think of a robot less like a thinking agent and more like a finely tuned instrument. A violin can produce extraordinarily precise sound, but only if it is played within the limits of its tuning. Stretch the strings too far, and the sound collapses. Robots behave in much the same way. Their accuracy exists only as long as the world remains close enough to what they expect. One of the quiet facts behind robotic precision is that it is never absolute. Every robot operates with tolerances, small, accepted margins of error. A movement might be accurate within fractions of a millimeter, but never exactly identical. Sensors fluctuate, materials expand and contract. Mechanical joints wear down over time. Precision, in practice, is managed imperfection. What makes robots impressive is not that they avoid error, but that they keep error contained. Each movement is calculated with an understanding of how much deviation is acceptable. If the deviation remains inside that window, the system continues. If it exceeds it, the system reacts. The boundary between success and failure is not a cliff. It is a line drawn deliberately by designers. This is why robotic precision often feels fragile. A robot can perform flawlessly for thousands of cycles, then suddenly stop because a single value drifts just far enough. To a human observer, this looks like failure appearing out of nowhere. In reality, the system has been approaching that boundary for a long time. A useful way to imagine this is to think of walking on a narrow path in fog. As long as the path remains straight, movement feels effortless. But the moment the path curves unexpectedly, balance becomes difficult. Robots experience the world in a similar way. They move confidently through familiar conditions and struggle when those conditions shift even slightly. Repetition plays a central role here. Robots are unmatched at repeating actions, but repetition amplifies small imperfections. A deviation that is negligible once can become significant after thousands of cycles. This is why robotic systems are constantly recalibrated. Precision is not set once and forgotten. It is maintained. Another fact often overlooked is that robots do not compensate for error the way humans do. A human adjusts unconsciously. A hand corrects its grip. A foot shifts balance mid-step. Robots cannot do this unless those corrections have been explicitly programmed or learned within strict limits. Outside those limits, the system either stops or continues incorrectly. This rigidity is both a strength and a weakness. It allows robots to achieve levels of consistency humans cannot match, but it also means that unexpected variation is dangerous. Precision depends on predictability. The less predictable the environment, the less effective precision becomes. In many robotic systems, precision is distributed rather than centralized. Accuracy does not come from a single perfect component, but from multiple imperfect ones working together. Sensors verify positions. Controllers calculate adjustments. Actuators execute movement. Feedback loops check results. Precision emerges from this conversation between parts. This layered structure is why robotic errors can cascade. A small sensor misreading may lead to a slightly incorrect calculation. That calculation may produce a small positional error. Over time, these errors stack. What began as noise becomes deviation. And deviation, once it crosses tolerance, becomes failure. Humans often imagine robotic error as dramatic, sparks, sudden collapse, obvious malfunction. In reality, most robotic failures are quiet. A robot stops moving. A process pauses. A system waits for intervention. Silence replaces motion. The absence of action becomes the signal that something has gone wrong. This quiet failure can be unsettling. Robots are expected to be reliable, and when they stop without visible reason, trust is shaken. Yet this behavior is intentional. Stopping is often the safest response. A robot that continues despite uncertainty is more dangerous than one that pauses. Another misconception is that robots always choose the most accurate option. In practice, robots often choose the safest one. Precision is balanced against risk. A movement that is technically possible may be rejected if it increases uncertainty. This is why robotic motion sometimes appears overly cautious. In shared spaces, this caution becomes more pronounced. Robots slow down near humans not because they lose precision, but because precision becomes secondary to safety. Movements are widened. Margins increase. Accuracy is deliberately relaxed to reduce risk. This trade-off can feel counterintuitive. We expect machines to outperform humans, not hesitate around them. But robotic precision is never independent of context. The same robot can behave very differently depending on where it is allowed to operate. A helpful metaphor here is handwriting. A person writing slowly produces neat, controlled letters. Writing faster introduces variation. Robots face a similar balance. Speed and precision exist in tension. Increasing one often reduces the other. Engineers choose where that balance should lie. Another subtle fact is that robots do not recognize almost correct. A position is either within tolerance or it is not. There is no sense of near miss or good enough unless explicitly defined. This binary evaluation is why robotic behavior can feel unforgiving. Over time, wear introduces further complexity. Mechanical components change shape microscopically. Lubrication degrades. Temperature alters material properties. Robots compensate for some of this through feedback, but not indefinitely. Precision must be actively preserved. This need for preservation explains why maintenance is inseparable from robotics. Precision is not a permanent trait. It is a condition that must be sustained. Without regular recalibration, even the most accurate systems drift toward failure. What often surprises people is how early these limits are considered. Robots are designed with failure in mind from the beginning. Engineers do not ask how to make systems that never fail. They ask how to make systems that fail safely. A robot that stops at the slightest irregularity may appear fragile, but this behavior reflects discipline, not weakness. High-stakes systems are designed to avoid acting beyond certainty. As robots become more capable, expectations rise, yet complexity introduces new risks. Additional sensors bring more noise. Greater flexibility brings more uncertainty, and precision becomes harder to preserve rather than easier. For this reason, reliability often favors restraint. Many critical robotic systems remain deliberately conservative, choosing simplicity over novelty. Innovation is introduced slowly and quietly because precision does not come from perfection, but from boundaries. Robots are accurate not because they are free, but because they are constrained, and they remain consistent only as long as the world stays within those limits. What often escapes attention is that robotic failure rarely begins where it becomes visible. When a robot stops, drops an object, or misses a movement, the cause is almost never that exact moment. The failure usually started much earlier, quietly, in places too small to notice. A fraction of a degree. a barely measurable delay, a sensor value drifting just enough to still appear acceptable. Robotic systems are built on the assumption that small deviations will remain small. Tolerances exist precisely for this reason. But tolerance is not forgiveness, it is containment. As long as errors stay within bounds, the system continues. When they accumulate, containment breaks. This accumulation is what makes robotic errors feel sudden. To a human observer, everything looks normal until it suddenly isn't. But the robot has been compensating all along, adjusting, correcting, rebalancing. Each correction introduces its own tiny cost. Over time, the system becomes increasingly dependent on compensation rather than alignment. A useful way to imagine this is to think of stacking sheets of paper. One sheet placed slightly off-center does not matter. Neither does the second or the third. But stack enough of them with the same offset, and the pile begins to lean. Eventually, gravity intervenes. The fall feels sudden, but the imbalance was always there. In robotic systems, this lean can appear in many forms. Mechanical wear changes how joints respond. Temperature shifts alter material behavior. Sensors slowly lose calibration. Software updates introduce new assumptions. None of these changes are dramatic on their own. Together, they reshape the system's internal reality. One of the reasons robots struggle with this kind of drift is that they do not perceive trends. They evaluate states, not trajectories. A value is either acceptable or not at a given moment. The fact that it has been steadily moving toward a limit is irrelevant until the limit is crossed. Humans, by contrast, are good at sensing gradual change. A person notices that something feels off long before it becomes wrong. Robots lack this intuition. They do not feel degradation. They detect violation. This difference explains why preventive maintenance is so critical in robotics. Maintenance is not about fixing broken systems. It is about resetting accumulated deviation before it becomes visible. Calibration routines do not improve performance. They restore assumptions. Another quiet fact is that robotic systems often hide their own instability. Feedback loops are designed to smooth output, masking internal correction. Motion looks stable even as the system works harder to maintain it. This makes early warning difficult. The robot appears fine until it is not. Error chains also reveal why redundancy can both help and hurt. Redundant sensors increase reliability by cross-checking data, but they also increase complexity. When sensors disagree, the system must decide which one to trust. That decision introduces another potential failure point. This is why robotic design often involves compromise rather than optimization. More precision in one area may reduce robustness in another. Tighter tolerances improve accuracy but reduce flexibility. Looser tolerances increase resilience but reduce repeatability. There is no perfect configuration, only trade-offs. Robotic precision becomes most fragile outside controlled environments. Dust, vibration, moisture, and human unpredictability introduce variability that robots are not designed to interpret intuitively. The system itself has not changed, but the world around it has. What was once stable becomes dynamic, and precision begins to erode, not through malfunction, but through misalignment between expectation and reality. In these conditions, failure often appears as hesitation. Movements slow, pauses lengthen, and stops become frequent. This is not confusion. It is protection. Each pause is an attempt to re-establish certainty within predefined rules. When no safe option exists, waiting becomes the only permissible action, even if that frustrates human observers who expect adaptation or improvisation. Many assume such failures occur because robots are not intelligent enough. In reality, they often fail because they are too specialized. Their strength lies in performing extremely well under expected conditions, not in handling change. For this reason, Robotic success depends as much on environment design as on the robot itself. Floors are marked, objects standardized, and lighting controlled to reduce uncertainty. When this shaping breaks down, reliability follows. Robotic error, then, is not an exception, but an assumption. Systems are built around the expectation of failure, with the goal of controlling its impact rather than eliminating it. As systems scale, sensitivity increases. Stopping too early is preferred over stopping too late. What looks like fragility from the outside is discipline from within. Robots do not fail because they are careless. They fail because they are exact, obeying limits without exception. And when the world no longer fits those limits, stopping becomes not defeat, but control. When robots enter spaces shared with humans, something subtle but profound changes. The machine itself may remain the same, but its behavior does not. Precision is adjusted. Speed is reduced. Confidence gives way to caution. Not because the robot has become less capable, but because the presence of humans introduces a new variable, one that cannot be fully controlled. Robots are not aware of people in the way people are aware of each other. They do not recognize intention, emotion, or social context. Instead, they detect signals. A shape enters a defined zone. A distance threshold is crossed. A movement pattern changes. These events are not understood as human actions. They are registered as conditions that require modification of behavior. This is why robots often slow down near people. It is not hesitation. It is compliance. Safety systems immediately alter allowable motion when human presence is detected. Forces are limited. Paths are recalculated. Margins widen. The robot becomes less efficient by design. One of the quiet facts about human-robot interaction is that humans are treated as uncertainty. Objects behave predictably. Machines behave predictably. Humans do not. A person may stop suddenly, change direction, reach unexpectedly, or behave inconsistently. For robots, this unpredictability must be assumed at all times. As a result, robots do not respond to what humans do. They respond to what humans might do. This difference is crucial. The robot is not reacting to intention, but to possibility. A raised hand is not a gesture. It is a potential intrusion into a safety envelope. This is why robots often appear overly cautious. A machine may pause even when a human seems safely distant. The robot does not calculate comfort. It calculates risk. And risk, in shared environments, is always treated conservatively. Humans, on the other hand, read behavior differently. We interpret pauses as uncertainty, slow movement as confusion, sudden stops as malfunction. These interpretations are natural, but they are often wrong. What appears awkward is usually deliberate. One of the most interesting dynamics in shared spaces is that robots are often more predictable than humans, yet humans expect robots to adapt to them. People step into robotic paths assuming the machine will stop, and it usually does. This reinforces the expectation. Over time, humans begin to behave less cautiously around robots, trusting their restraint. This trust is dangerous if misunderstood. Robots stop not because they understand responsibility, but because they are required to. If a condition falls outside programmed expectations, the response may not align with human assumptions. Another quiet fact is that robots often have multiple modes of behavior, depending on whether humans are nearby. The same robot may move quickly and efficiently when alone, then slow dramatically when people enter the area. This shift can happen instantly, without warning. To an observer, this can feel like a personality change. In reality, it is a rule change. The robot has entered a different operational state. Nothing about its understanding has changed, only its permissions. In many systems, robots are deliberately made to look less capable around humans. Movements are smoothed. Trajectories are exaggerated. pauses are inserted. These choices are not technical necessities. They are design decisions meant to make behavior legible and reassuring. Legibility matters. Humans feel safer when they can anticipate motion. A robot that moves too efficiently may appear threatening simply because its intentions are unreadable. Slower, more expressive motion reduces anxiety, even if it reduces productivity. This reveals an unusual truth. In shared spaces, robotic success is measured not only by performance, but by perception. A robot that completes tasks efficiently but unsettles people is often considered less successful than one that works more slowly but feels understandable. Distance plays a critical role here. Robots track proximity continuously. Invisible boundaries surround them, expanding and contracting depending on speed, task, and environment. Crossing these boundaries triggers behavioral changes. What is rarely noticed is that these boundaries are asymmetric. A robot may allow objects closer than it allows humans. The same distance means different things depending on what occupies it. Humans are given larger margins because their behavior cannot be predicted precisely. This asymmetry can feel strange. A robot may brush past a machine confidently and halt abruptly when a person approaches. The robot does not value the person more. It simply lacks confidence in predicting human movement. Another factor shaping interaction is line of sight. Robots often assume that if a human can see them, the human can avoid them. When visibility is reduced, caution increases, paths change, speed drops. Waiting becomes more frequent. Sound also plays a role. Many robots emit subtle noises, not as alerts, but as signals of presence. These sounds help humans locate machines without looking directly at them. Silence, while efficient, can be unsettling in shared environments. Robots treat physical contact not as interaction, but as error. Touch immediately triggers stops or retreats because it signals a boundary violation, not communication. Even so-called collaborative robots do not truly collaborate in a cognitive sense. They simply coexist safely with humans by limiting force, speed, and proximity. Humans, meanwhile, adapt quickly. We learn robotic rhythms, anticipate movements, and unconsciously adjust our behavior to accommodate machines. Robots rarely return this adaptation unless explicitly programmed to do so. Over time, this imbalance makes robots appear more intelligent than they are because humans reorganize themselves around fixed systems. As robots become more visible, perception drifts further from reality. People instinctively read intention, politeness, or hesitation into rule-based actions. Robots neither confirm nor deny these interpretations. They remain systems designed to manage risk among unpredictable agents, defined not by intelligence, but by restraint moving slowly, pausing often, and giving way whenever caution demands it. What changes most dramatically in shared spaces is not the robot, but the human. The longer people spend around robots, the faster familiarity replaces caution. Movements that once felt unusual become background noise. Pauses are no longer noticed. Slow turns and sudden stops stop feeling strange. What was once interpreted carefully becomes assumed. This shift happens quietly. Humans are exceptionally good at pattern recognition, and once a robot's behavior becomes predictable, the mind stops monitoring it actively. The machine fades into the environment. It becomes furniture with motion, infrastructure with presence. At this point, risk does not disappear. It becomes invisible. One of the most important facts about human-robot interaction is that safety systems are designed for attentive humans, not indifferent ones. They assume that people will notice boundaries, respect signals, and remain aware of shared space. As familiarity grows, these assumptions weaken. People step closer than before. They cross paths without looking. They reach into zones they previously avoided. The robot still responds correctly, but the margin for error narrows. Safety shifts from being shared to being one-sided. This is where many systems become fragile. Robots do not understand increasing confidence. They do not detect complacency. A human behaving more boldly does not register as intent or recklessness. It is simply another movement to be processed until it isn't. A useful way to imagine this is to think of traffic in an unfamiliar city. At first, every intersection demands attention. Signs are read carefully. Speed is adjusted. Over time, familiarity sets in. Drivers take shortcuts. Attention drifts. Accidents rarely happen on the first day. They happen when the environment feels safe enough to ignore. Robots encounter humans in a similar way. Early interaction is cautious. Later interaction is casual. The system does not change its rules, but the human interpretation of those rules does. Another subtle factor is trust transfer. When a robot performs safely once, that trust is unconsciously extended to future situations, even when conditions are different. A delivery robot that stops reliably in one setting is assumed to behave the same way everywhere. A collaborative arm that yields gently once is expected to do so again, regardless of context. This expectation is dangerous because robotic behavior is conditional, not moral. The robot does not decide to be careful. It follows rules that may not apply in every configuration. When conditions shift, behavior shifts too, often without warning. One of the least discussed facts about shared robotic spaces is that robots rarely signal uncertainty. Humans communicate uncertainty constantly through hesitation, tone, posture. Robots do not. When a robot slows or pauses, it is not expressing doubt. It is executing a predefined response. This makes it difficult for humans to distinguish between caution and malfunction. A pause might mean recalculation, or it might mean the system has reached a limit. To the human observer, both look the same. As robots become more common, people begin to assume they are more capable than they are. Visibility creates confidence. Repetition creates comfort. Comfort reduces attention. This is why many incidents involving robots occur not during complex operations, but during routine ones. The environment feels understood. The machine feels familiar. The human stops anticipating deviation. Another factor shaping interaction is responsibility diffusion. When robots handle tasks reliably, humans subconsciously offload vigilance. The robot will stop. The system won't allow that. These assumptions feel reasonable until the system encounters a situation it was never designed to handle. Robots do not escalate concern. They do not warn emotionally. They either continue or stop. When humans expect graded responses and receive binary ones, confusion follows. This binary nature also affects how humans attribute blame. When something goes wrong, the robot is often seen as having failed, even if the failure resulted from human behavior drifting outside safe assumptions. The machine becomes the visible actor, while the invisible system design fades from view. Another quiet fact is that robots change how humans move through space. Paths bend, standing positions shift, waiting patterns emerge. Over time, environments reorganize themselves around robotic behavior. This adaptation often happens unconsciously. Humans slow down near robots, or sometimes speed up to get past them. They learn where robots usually pause, where they turn, where they wait. These learned behaviors feel intuitive, but they are fragile. A software update or a slight change in layout can invalidate them instantly. Robots, meanwhile, do not remember past interactions. A human who has worked around a robot for years receives no special recognition. Experience is entirely on the human side. The robot treats every interaction as new. This asymmetry creates a subtle illusion of relationship. Humans feel familiarity. Robots do not. As systems scale, this illusion spreads. Public robots interact with thousands of people each day. and each person unconsciously assumes continuity based on past encounters. The robot, however, resets every time. Familiarity exists only on the human side. As robots become safer and more refined, expectations rise. Minor delays start to feel like flaws, brief stops like incompetence. This is the paradox of trust. The more reliable a system becomes, the less forgiving humans are when it fails. At the same time, robots struggle to signal context. A slowdown caused by human presence looks identical to one caused by sensor uncertainty. Designers add lights, sounds, and gestures, but these signals indicate state, not meaning. Intention is still projected, not communicated. Over time, shared spaces quietly reshape themselves around machines. Paths widen, movements become predictable, and humans adapt without noticing that order has replaced spontaneity. As reliance grows, assistance starts to feel like agency and vigilance fades, not at first contact, but with comfort. Robots do not adjust to this shift. They continue within fixed constraints until those limits are crossed, at which point motion stops and the illusion breaks. In shared spaces, consistency belongs to machines. Judgment must remain human. When robots disappear from view, they do not become inactive. In many ways, this is when they begin their most characteristic work. Away from human presence, away from observation, robots settle into environments designed entirely around their needs. There are no pauses added for comfort, no exaggerated movements for clarity, no concessions made for perception. What remains is function in its quietest form. Most robotic labor happens without an audience. At night, when buildings empty and lights dim, systems continue operating with the same consistency they showed during the day, often faster, more efficiently, and with fewer interruptions. The absence of humans removes uncertainty. Safety envelopes contract. Speed increases. Motion becomes confident, almost indifferent. This shift is subtle but fundamental. The robot itself has not changed. The rules governing it have. When humans leave, entire layers of constraint fall away. What remains is a machine interacting with an environment that behaves as expected. Floors do not move unpredictably. Objects remain where they were placed. No one steps into paths or reaches unexpectedly. For robots, this is an ideal world. Factories are the most obvious example, but they are far from the only one. Beneath cities, robotic systems monitor water flow, pressure, and temperature continuously. In data centers, machines regulate cooling, airflow, and power distribution with minute precision. In ports and logistics hubs, robots reposition containers, track inventory, and optimize routes long after human workers have gone home. In these environments, robots rarely stop unless something truly unusual occurs. Waiting still exists, but it is functional rather than protective. The system waits for input, not permission. The difference matters. One of the least visible aspects of robotics is how deeply embedded machines have become in infrastructure. Many robotic systems are not recognizable as robots at all. They do not move through space. They do not resemble tools or machines in the conventional sense. They exist as automated processes that sense, adjust, and respond continuously. These systems often operate for years without direct human interaction. Maintenance schedules are planned long in advance. Monitoring happens remotely. Alerts are triggered only when thresholds are crossed. In the meantime, robots perform the same actions thousands of times, unnoticed. This invisibility shapes how societies think about robots. Machines that are seen are debated. Machines that are hidden are assumed. The robot that delivers a package draws attention. The robot that maintains power stability does not. Yet the second may affect far more lives. Different countries approach this invisible robotics landscape in different ways. not because the technology itself is radically different, but because priorities are. In some regions, robots are concentrated in manufacturing, where efficiency and consistency are paramount. In others, robotics is directed toward logistics, infrastructure, or public services. In Japan, for example, a significant focus has been placed on robots that operate reliably in long-term, unattended contexts. Aging infrastructure and demographic shifts have shaped this emphasis. Systems are designed to work steadily, predictably, and with minimal intervention over extended periods. In parts of Europe, robotic systems are often integrated into infrastructure with an emphasis on safety, regulation, and coexistence. Automation is introduced gradually, with strong constraints and extensive oversight. Robots here tend to operate conservatively, prioritizing stability over speed. In the United States, large-scale robotic deployment has often focused on logistics, warehousing, and data-driven optimization. Systems are designed to scale rapidly, adapt through software updates, and integrate with complex networks. Visibility is secondary to throughput. In China, robotics has expanded rapidly across manufacturing, logistics, and urban infrastructure. Scale is a defining feature. Systems are often designed to operate continuously across vast environments, where efficiency emerges not from individual precision, but from coordination across thousands of machines. These differences are not ideological as much as practical. Each reflects local needs, labor structures, and economic pressures. The robot itself remains the same kind of system everywhere. What changes is the context it serves. Another quiet fact about unseen robots is that they are often more autonomous than visible ones. Not in the sense of intelligence, but in duration. A robot working in a closed environment may operate for weeks without interruption. There is no expectation of interaction, no requirement to explain behavior, no need to pause for reassurance. This extended autonomy creates a different rhythm. Maintenance becomes predictive rather than reactive. Systems are monitored through trends rather than events. A deviation is noticed long before it becomes failure. Time behaves differently here. Days blur into continuous operation. There is no beginning or end to a task, only steady continuation. Robots do not complete jobs. They sustain processes. Away from human presence, robots operate in a different relationship with time. Tasks have no clear beginning or end. There is only continuation. Whether maintaining infrastructure beneath cities, managing power grids, or operating in extreme environments like deep oceans or space, these systems are not assistants but extensions of human reach. Their work is quiet, repetitive, and constant, built around verification and adjustment rather than visible action. Reliability here is not impressive, it is essential. Because these robots remain unseen, they age and fail differently. Wear, sensor drift, and degradation are managed gradually through recalibration and maintenance. Failure is delayed, often indefinitely, and rarely dramatic. Success is defined by absence. Nothing breaks, nothing stops, nothing draws attention. Trust forms without familiarity, and dependence grows without awareness. People rely daily on systems they never directly encounter, interacting not with individuals, but with patterns, flows, demands, and trends. At scale, robotics becomes less about machines and more about structure. Fleets replace individuals, redundancy replaces personality, and coordination replaces identity. When systems fail, disruption briefly exposes what was hidden, then invisibility returns. Regulation reinforces this quiet stability, favoring reliability over novelty. As a result, many of the most advanced robotic systems appear boring, unchanged, and unnoticed. Yet they sustain modern life continuously, proving that robots are often most powerful when they are not seen at all. They do not wait for meaning. They do not seek recognition. They do not adapt to expectation. they continue. And in that continuation, quiet, persistent, and largely invisible, the real scale of robotics becomes clear. Not in what we see, but in what keeps working while we look elsewhere. When people imagine robots, they rarely imagine the systems that work unseen. The image that comes to mind is almost always physical. Arms, legs, a body that moves through space, a machine that occupies a place in the room. This image is powerful, not because it represents the majority of robots, but because it aligns with how humans understand presence. Robots with bodies demand attention. A mechanical arm swinging into motion. A humanoid machine taking a step. These forms feel significant because they echo us. Movement that resembles human movement is immediately interpreted as intention, even when none exists. This is why collared robotic arms in factories became iconic long before most people understood what they actually did. They were visible. They moved decisively. They occupied space in a way software and infrastructure never could. For many, they became the definition of robotics itself. Yet even these robots, familiar as they are far rarer than imagined. A single robotic arm may represent millions of lines of code, layers of safety logic, and years of engineering effort. They are expensive, delicate, and demanding. Their environment must be carefully shaped around them for them to function reliably. Humanoid robots push this even further. Giving a robot legs, balance, and a human-like form multiplies complexity. Walking alone introduces challenges that wheels and fixed bases avoid entirely. Balance must be calculated continuously. Surfaces vary. Unexpected contact becomes dangerous. Energy use increases dramatically. This is why most humanoid robots remain experimental. Not because the idea is flawed, but because the cost of making them reliable is immense. Every additional degree of freedom introduces new failure modes. Every attempt to mimic human versatility reduces predictability. The irony is that the more a robot resembles a human, the less suitable it becomes for most tasks. Human bodies evolved for adaptability, not efficiency. Robots excel when they abandon that form. Wheels outperform legs. Fixed arms outperform hands. Specialized tools outperform general-purpose limbs. Still, humanoid robots persist in imagination and research for a reason. They represent a question rather than a solution. Can machines navigate spaces built for humans without forcing the world to change? Can robots enter our environments without redesigning everything around them? So far, the answer has been cautious. Progress is steady but restrained. Humanoid robots walk slowly. They move deliberately. They fall often. Each success is meaningful, but each failure reminds us how narrow the margin is. This restraint contrasts sharply with unseen robotics. Infrastructure systems do not need to look familiar. They do not need to move like us. They only need to work. And so they do quietly, continuously, and without ceremony. The difference between these two worlds reveals something important. Visible robots are judged by presence. Invisible robots are judged by absence. One is noticed when it moves. The other is noticed only when it stops. Countries navigate this balance differently. Some invest heavily in humanoid and service robots to address demographic change and social needs. Others focus on logistics, manufacturing, and infrastructure, where form is irrelevant and efficiency dominates. Neither approach is more advanced. They simply answer different questions. What unites all of these systems is that none of them seek recognition. Robots do not aim to impress. They do not aspire. They do not wonder whether their work matters. They execute what they were built to do, and nothing more. The robots that shape daily life most profoundly are rarely the ones we talk about. They are the systems that keep water flowing, power balanced, data moving, and goods arriving. They work while we sleep and adjust while we look elsewhere. Their success is measured not by visibility, but by continuity, by the fact that nothing demands our attention. The robots we notice, with arms, legs, and faces, serve a different role. They anchor our imagination and give form to an otherwise abstract transformation. They make robotics visible, even though they represent only a small part of its true scale. In this sense, visible robots are the surface, while invisible robots are the structure beneath. And structures do not announce themselves. They endure quietly and become noticeable only when they fail. As robotics continues to expand, more systems will disappear into the background. Processes will automate without ceremony, and the world will feel mostly the same until it doesn't. When a robot stops, we notice. When it continues, we forget. This forgetting is not ignorance, but integration. The robot becomes part of the environment rather than an object within it. And perhaps that is the final quiet truth of robotics. Not that machines are becoming more like us, but that we are learning to live inside systems that no longer need to be seen to be real.